Welcome to Megger's monthly webinar series. Today's topic is Guide to Underground Fault Locating. In this session, we will be discussing the basics of underground fault locating and some best practices that you can use to locate your faults more efficiently in the field. My name is Greg Valdez. I am the Marketing Communications Manager for Megger North America, and I'll be acting as the moderator for today's presentation. I will be supporting you on any technical issues or questions for our presenter during the session. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segments. You will receive a copy of the presentation afterwards and a link to the recorded session if you want to watch it again later or share it with your colleagues. Remember, you can ask questions at any time during the presentation, and I will interject them as we have time. Our presenter today is Robert Probst, Application Engineer for Cable Products. Robert is based out of our Dallas office in Texas. Today we are also joined by Henny Ogen. He is our product manager out of Valley Forge. He actually is the product manager for our cable products. Thank you for joining us today, and take it away, Robert.
Good morning, everybody. My name is Robert. I'm one of the applications engineers based in Dallas for the cable products. Before I start, I joined Megger approximately a year ago. So far, I had limited field experience. This is why I got support by Henning, and I think a lot of you people know Henning. He is an authority figure in cable fault location. So whenever my limited knowledge is not enough to answer your questions, I will direct it to Henning, and I hope Henning can help me with that.
No problem.
Okay. So let's start with the motivation for cable fault location. When there's a fault happening in the field, what is the objective that we are trying to address here? And of course, it is to find the fault and then take appropriate measures. The problem with this is it's not a straightforward process. You're typically under pressure. You have to find it quickly, but you also have to find it safely. Nobody should be harmed. And it is not so much a straightforward engineering process or something like that. It is more a troubleshooting process. And for this troubleshooting process, there is no single method that applies to everything, that can solve every problem and that can find any fault. So you have to work with a toolbox of various techniques. And the trick is, the solution to the problem is to apply the one method that works. And a few of those are outlined in this presentation. Another thing on the agenda, initially I wanted to include a few more methods, but due to time restrictions, I had to cut some of them out. And there's probably a possibility in the future to do like another webinar that is kind of an advanced fault location webinar, covering the techniques we don't have time to cover today. So what we will talk about is, on the very left, you will see kind of the introduction to the topic, and you will realize that the other three boxes that you see, the yellow one, the pink one, and the green one, is the actual fault location process. So let's start with the gray box on the left. Very important always is safety. Always work as safely as possible. Your company probably has rules, and you always have to comply with those rules. But typically, cable fault location, you work on a de-energized cable that is to be properly grounded. And there's always sources that can endanger personnel that is working around a cable fault. First of all, you have to make sure that the cable is actually de-energized, so the operating voltage is one of the main hazards. There could be risk of backfeed. More and more common that people have generators at home that could backfeed, so this is a problem. Then you have induced electromagnetic interference from adjacent circuits or whatever is also in the trench or substation. And of course, the equipment itself is a high voltage equipment, so you have to be careful to use that equipment in a proper way as well. One word for in terms of grounding. Typically, the modern philosophy is that you have a single point grounding, so one system ground only. That means you should always verify that you have a true earth ground and your grounding scheme is not floating. Actually, you think you're grounded, but you're not. So always make sure there's somewhere a true earth ground that you choose as system ground. On a pad mount transformer, that would be the ground rod typically. Then on the equipment, you typically have an equipment safety ground. That is only there to discharge any energy that is still stored in the equipment in case of a fault, and that the enclosure is not on potential and potentially harming people. Then you have the high voltage return, which connects to the shield. We will get to the cable construction in a second. And you have the actual high voltage connection that typically connects to the conductor of the cable. And you should always establish these things in the order, like when you connect from top to bottom, when you disconnect from bottom to top. So the grounds are typically the last thing you want to take off. Now, in general, talking about cables, to have the same language here, a typical construction would be you have a center conductor, aluminum in most of the cases. Then you have a semiconductive layer around it that is there to smoothen out the field around the center conductor, because the center conductor is made out of strands and it's not a nice even surface, and that semicon layer is there to smoothen out the field. So there's no sharp edges or points where there could be a high field stress. Then you have the main insulation. Then you have another semicon layer around the main insulation, which should provide a smooth transition from the main insulation into the actual metallic shield or concentric neutral. Some people call it drain wires, but the metallic shield, the return, the high voltage return, then is typically surrounded by a jacket. There is unjacketed cable, which is a particular problem, but today most of the cables installed are jacketed or should be jacketed at least. Now, talking about cable constructions, they come unfortunately in a big variety. We start on the left. This presentation does not really deal with the secondary fault location and the low voltage stuff, but this is what you would typically see on low voltage installations, the segmented cables. Then in the middle, you have the shielded concentric cable, and this is the main type of construction in the medium and the high voltage world. So you have one conductor, then you have some sort of insulation, and then you have the shield, the stranded concentric neutral or tape shield, as we will see in a minute. And a typical failure mode is a fault between the core and the shield. Just for nomenclature, if you have a fault from the shield to the earth, that would be called a sheath fault. Then you have a three-phase version of this very construction. So you have three of those shielded concentric cables in one surrounded with filler material, and then in a lot of cases an armor around it, which is for mechanic protection. For those cables, the core-to-core fault, like the phase-to-phase fault, is unlikely because each cable is surrounded by a concentric by a shield, and each conductor has its own shield. So the electric field is symmetrical. It's also called a radial field cable. And then on the right, you can see the dominant type of construction for PIL cables, and when cable installations were pretty much being being conceived as electrical connections. So this is pretty much the oldest way of constructing a cable. You have three conductors, but they only have one common shield. And then that leads to certain problems. The field is not symmetrical, so the stress is not distributed symmetrically. And here you can have various different scenarios also for the fault, which can be a face-to-face. And but as I said, this is predominantly for the laminated cables, for the PIL cables. And so this doesn't really apply for extruded cables. So for everybody who's not familiar with that, what do I mean by this? Like typically extruded cables, this is plastic cables, and you have two main types. You have the EPR type, ethylene propylene rubber, and you have the XLPE, the cross-linked polyethylene. And to the right you can see the PIL cables. This is laminated insulation. It's completely different, a completely different type of constructing an insulation, while on the left this is actual solid dielectric. The PILC is layers of paper impregnated with oil, and fault location on those cables is much different. And these cables are typically used in downtown networks, while the two or the plastic cables, the extruded cables, are typically used in so-called URD systems, or in general in just standard distribution systems. So on the left you can see these three pictures that you have here. You can see just different types of neutrals. So you have a stranded neutral, that means it's like separate wires. Then you have a tape shield in the middle, which is literally a tape instead of concentric, instead of wires. And the unjacketed, that's a problem. There, the neutral is exposed to the elements because there's no jacket around it. And certain fault location methods can get into trouble with this because it's not so easy.
Robert? Okay, now I see the pictures. Okay, good. Okay.
Oh, okay. There was a delay.
Yeah, there was a delay to bring up the two pictures. Maybe you just want to give a little time for everyone to see it on that previous slide.
Okay, 1 second.
Yeah.
So it's visible now for you?
Yeah.
Okay. As I said, on the left you can see the wires, actual wires. Then you have the tape in the middle, and the unjacketed cable. I only found like a picture, not so much an illustration. And what you see there, this gray, this is the corrosion of the actual neutral. And this stuff can actually corrode away. It can be literally eaten away by the elements, by chemical reactions in the soil, and that can cause problems. Just speaking in general, so we have an understanding what we're actually talking about here. When people say, for instance, 15 kV cable, everything in the power industry is always rated three-phase. Nameplates, it's typically referring to three-phase. So that means this 15 kV is actually a system voltage. That means it is a face-to-face voltage. Now, if you have a cable fault and only one phase is faulted, and the other two cables are not, then the problem there is each individual cable does not see the 15 kV, even though it's referred to it as 15 kV cable. Because the conductor and the potential difference is between the conductor and the neutral, the return. Now, if you have face-to-face, that is 15 kV. The actual cable is only, the main insulation of each individual cable is only exposed to √3 less. That means from the center conductor to the neutral, a 15 kV cable sees 8.6 at the most. A 25 kV cable, this number is 14.4 kV, and for a 35 kV cable, this is 20.2 kV. At its max. There are a lot of utilities or co-ops. They would not even go to the 8.6 kV in terms of the 15 kV cable, for instance. Their operating voltage would be 7.2, and that comes out to less than 15 kV face-to-face. Now, when you have a fault, you expect that the voltage, when you apply voltage to the cable, that this breakdown voltage, as we call it, is lower than this operating voltage, because whatever made the cable fail the night before, the day before, the week before, you expect this to be less, because it should have been good for the operating voltage. And there is another thing that is related to this problem, is the insulation thickness, because as we will see, certain methods rely on the ability to actually create a flashover artificially at the fault location to locate the fault. And the air gap distance, that means the distance between the conductor and the neutral, can play a role in that. Now, just a few things that determine the behavior of the cable, or what makes the cable work. So the cable has a capacitance. That capacitance is proportional to a few parameters, I would call it, physical, mechanical design parameters. So this the epsilon that you see here, that's a typical abbreviation for the material of the main insulation. For XLPE, this is typically 2.3 or 2.4. Of course, the length is important for the capacitance, and then also the capacitance is inversely proportional to the different radiuses that you can find there. So the outer to the inner. So the inner would be here the conductor, and the outer would be the actual thickness of the main insulation. And you can see it's not a nice number. There's some crazy math there, and that only pretty much determines that if you would plot the field strength and the voltage distribution starting from the center conductor to the neutral, that this is not linear. It's not a nice straight line in the diagram. The closer you get to the center conductor, the more stress the insulation is actually experiencing. Then we have something that I will go into detail later, but it's the cable velocity, the velocity of propagation, and the velocity v is mainly a function of the material. I will talk about this a little in detail later. Just for now, it's just important to understand that different materials and have different cable velocities. So a PILC cable, for instance, has a different propagation velocity than an XLPE or an EPR. And then we have the impedance. Now, don't be scared by the math in case you're not a math guy. This is pretty much important later for some of the prelocation methods. The impedance is determined by two things mainly. There's a material influence, which is the resistance. So you cannot flee the resistance of the cable, and then the quality of the insulation, that is what's in that G. But take a look at this L and at this C. These things are predominantly, this is a geometric quantity. So the inductance and the capacitance, as it is called, this is completely determined by the geometry, and we can use this effect later on when we want to do TDR measurements. So now let's talk about faults. So you can classify the faults into mainly by the resistance. But I wanted to take a little bit of a more practical approach. So the most common fault in typical medium voltage cables is a pinhole fault. It's a high resistance fault that is at least in the kilo ohms. What you would expect on the breakdown voltage, remember, I was talking about this a few slides ago. Let's say on the 15 kV cable with this 8.6 max, you would expect this to be lower, and typical values that we see in the field is 4 to 8 kV. So, by from a physical view, this means the center conductor is still continuous, so it's not severed or anything. It's still all the way there, and it does not have any contact physical contact with the concentric neutral, but there's a hole in the insulation, and that made the cable, or that was the result of the cable failing, of that blowout that happened. There's another fault. It's an open conductor, and that pretty much means the conductor was either severed, like it was torn apart, or it burned open. The problem with this is, and we will get into this, what all these abbreviations mean, a TDR or a radar cannot see beyond this point because it relies on the ability to have to actually use the conductor and the return to measure certain parameters of the cable. And you may also not be able to use the what's called the arc reflection method, especially if that gap is too wide, so you cannot make it flash over. And the typical solution in the practical world would be, okay, if you limit it to this point, just go to the other end of the cable, because typically the cables, as we discussed, isolated, grounded, stood off, parked. So you can go to the other side and try your fault location techniques from the other side and hope, to learn more. And then we have a short. This typically happens when the center conductor and the concentric neutral, when they are in direct contact. This could also be by metal pieces. And the example would be somebody installed a ground rod somewhere, or a stop sign was installed, and so they hit a cable. And then, because they go right through the cable, the center conductor and the neutral are touching pretty much. They have an electrical connection. And these are low resistance, very low resistance faults, 10 ohms, 100 ohms typically. The problem also with those faults is, I just want to mention it, since it's a short, you will later see that there's no possibility to create a flash over there, a spark. And so you also cannot use really the arc reflection method on those faults. Now, when I said URD, because this abbreviation was mentioned a couple of times now, URD stands for Underground Residential Distribution. And when you think about what I tried to describe earlier with the plastic and the pill cables, everything that is in downtown networks with these lead cables, the laminated cables, is pretty much the opposite of URD cables. So URD cables are typically XLPE or EPR, while downtown is mainly pill. The system voltages that we have in the US here are 15, 25, and 35. The kind of network type that you find in the utility world and in the distribution world here is loop feeds, or sometimes radial feeds. That means you have, like, from one point it goes radially from that point, or you have a loop with a normally open point. So you have access from two sides at least. Typically, those are single-phase cables, and that was in that overview with the 5 different construction types, the one in the middle, the pretty much the easiest kind of. You have one center conductor, main insulation, and a return. So URD systems, therefore, are what you can call, it's a point A to point B network or connection, and you rarely see branches, maybe a T-splice here and there, but downtown networks are typically, it's a branch network. So the URD systems are ideal for radar or TDR-based technologies because there is no problems with the signals being split up into the branches. Also, compared to any downtown network, URD systems are generally easy to access and fairly easy to isolate. The main failure mode for plastic cables, as it turned out over the decades, are so-called water trees. That means there's concentrations of water within the solid insulation, and at a certain point they will cause stress and electrical trees. And those electrical trees, they will grow forward at a very high rate and then make the cable fail. And the typical failure modus, since this happens very punctually, like very locally, is that the cable blows out and you have these pinhole faults. For URD networks, you can get away with kind of portable thumpers. You do not need big van-mounted systems most of the time. And the typical approach to fix those systems is you have to fault locate, and then once you have your fault location, you dug up the cable, you repair it, then you test it, and then you rebury it. While in downtown networks, that is not so easy. You have conduit, and the oil impregnated insulation it's a different animal entirely. So we're talking URD systems here. If you are interested in fault location in branch networks, Mr. Derek Smith, the area sales manager for the East Coast for the cable products at Megger, he did a webinar fairly recently solely on fault location on downtown and branch networks. So you may want to go there if you're interested on the other side, and when you want to see what the differences are between the URD and the downtown networks. So what is the fault location sequence? As I said, the three boxes are here again. So what I called here on the left pretty much the checks is what you do when you arrive and you want to learn what the actual situation is. By today's philosophy, probably the and not so, let's say, systematical approach would be just to get the search generator, the thumper out, and start thumping the cable, searching the cable, and hoping for the best. Today we have so many more tools, and all these tools are made to help you, to make your life easier as a fault locator, so why not use these tools? And since fault location is also a troubleshooting process, your toolbox must consist of various tools, and if you use them nicely, with every tool you gain some information that helps you to make a conclusion and find the fault much easier. So we have some checks, which is insulation resistance, then a high pot, then maybe tracing the cable, even though that is recommended, not necessary if you have good maps and you feel confident. Then we have the big block of prelocation, and within the prelocation we find the radar, the TDR, then the art reflection methods, and then other methods which are more complicated. And once you're done with the prelocation gives you an approximate distance to the fault in like very high accuracy, plus minus 1% in that range, but you never would dig a hole just based on the prelocation. So then the actual location, the pinpointing, takes place, and you use what a lot of people are familiar with out there. You have a thumper, and they use some sort of pinpointing device with the thumper together to actually pinpoint the fault. So what are the checks? Insulation resistance, particularly helpful just to get an idea of what is going on and to get an idea on the resistance of the fault. So do we have like a low resistance fault, a high resistance fault? Low resistance fault could indicate a short or a near short. High resistance, a pinhole fault. These things you can find out with an insulation test. If you have a three-phase cable in one jacket, you could do face-to-face checks to find out if there's something going on like this. So it's a very basic measurement that can already tell you a lot. So then you can do what a lot of people refer to a high pot test, but it's not like a classical high pot test. Before I came to Megger, I worked at a high power lab, and so a high pot has different meanings in different worlds. So here we're talking about it is a verification test for breakdown and to determine the breakdown voltage. It's not a test, it's not a withstand test, it's not a pressure test. So what we can gain, we can find out, can the cable hold voltage? If not, then you're probably on the correct cable, or at least you are on a faulted cable. Then you can see, is there a short? How do you see this with that kind of test? Well, if the voltage is not building up and you see a lot of leakage, that indicates that there's a fairly low resistance somewhere on the cable. That also determines, can I use the most popular prelocation method, the arc reflection method, or not? In certain fault configurations, you cannot use the arm. It's just not working physically. And of course, you determine the actual breakdown voltage, which later is important because all the high voltage techniques that you are using are based on that value, because you have to exceed that value to actually make the method work. And of course, as I said, as a recommended step, you can trace the cable. But if you are confident that your maps are accurate and there's no surprises waiting for you, it's not a must-have. So prelocation, we're in that pink box. What is prelocation? Typical methods are TDR. Then you have the arc reflection methods, which there is a few of those nowadays. Then you have bridges, which unfortunately I had to leave out of the presentation, so I cannot really say anything to that. But just to give you an idea, bridges are typically for the faults where you cannot use the arc reflection methods and you cannot use the TDR. So they fill a specific niche, and pretty much the territory in between a very low resistance fault and a high resistance fault that cannot addressed with the arc reflection method. And then there are other methods, like for instance the ice method or the decay method. That is all prelocation. So let's start with the TDR. What does TDR mean? TDR means Time Domain Reflectometry. And as the name says, it is a technique that works in the time domain. That means the instrument starts and stops clocks and measures reflections. It sends pulses into the cable and it interprets reflections based on in the time domain. So it's not in the frequency domain or in some other quantity. It is times. So you start a clock and you stop a clock. It is usually a low voltage, high frequency pulse. We're talking 20 to 30 volts. There's only one exception to that. There's one arc reflection method which utilizes a pulse that can be 1,000 or 1,500 volts in that range, but that is the only exception. It's typically a low voltage pulse. And in terms of physics, the TDR works based on, I have two parallel conductors and I send the pulse down. And just to clarify this, the actual electromagnetic pulse, that pulse that travels down the cable travels between those two conductors. So these conductors are too far away. Your 20, 30 volts, they get diminished, so you don't see much. That's one problem. So you need a fairly close return conductor to make that work. And so the pulse travels in between, and it travels at the wave propagation or velocity of propagation. So this is what I mentioned before. For different materials, the values can be different. And as I said before, this L and the C in that formula of the cable's impedance are purely defined by the geometry of the cable. This is the same for the inductance and the capacitance of an overhead line, and it's very much true for a cable. So the distance between those two conductors in terms of our single phase cable, which is the center conductor, and the concentric neutral, is proportional to its impedance. So the TDR, by sending down those signals, high frequency signals, will give you an impedance fingerprint of the cable with a low voltage measurement. And today's TDRs are much more evolved than 20, 30 years ago, and they can visualize actually that trace, which is way more important than actual just giving you a footage, like a distance, a numerical value. Your cable end is somewhere there. Because with the visuals, the human brain is very good in pattern recognition, and when you see something, when you can visualize this impedance footprint, you can gain a lot of additional information. So what kind of signatures do we have? So you look on your screen, so you connect the one lead of the TDR to the center conductor, the other lead to the return. If there's no change in impedance, that means there's nothing going on with the condition of the center conductor and the neutral, it's a flat line. If you have a high impedance situation suddenly, for instance, the distance between the two conductors are widening, or you hit the end of the cable, you will see an upward signature, an upward bump. If you have a low impedance situation, short, or the distance between the conductor and the concentric neutral is decreasing, you will see a downward signature. And since cables are made out of reels with a finite length, cables are spliced together, so there is a signature for splices. Transformers look the same, and you can see this is this S shape I have put on the bottom of your screen. So that is kind of an indication for a splice or a transformer. Now, how does this look in real life? This is a real life trace, and you can see in front you have some distortion. This is called the characteristic hookup impedance, because you have leads, the distance between the two leads change until you are actually connected to the cable, and this is reflected by this kind of wave shape to the left, and then nothing happens pretty much. 1/3 to the from the left, if you can see that there's a small signature, that would be a splice, this flat S shape, so there's a splice most likely. And then nothing happens to that cable, it's a flat line, and at the end you have this big upward signature, and the algorithm in the TDR puts a flag there and tells you the cable's open at 550 feet. Now the thing with this is you can have several systematic errors in there. If you have the wrong cable velocity, then this number will be off. So very important, and this is why I mentioned it's a troubleshooting process. It's not like you hook it up and a magic box is doing the cable fault location for you. That just doesn't exist. It is important that you have an expectation when you go out there. If you know the cable is 1,000 feet long and the TDR tells you 980, does this meet your expectation? Or does it not? Is it close to the 1,000 feet, or do you have a very exotic fault that is right there at 980? There's an open conductor or something like that, and you don't actually see the physical end of the cable. But 980, 990 out of 1,000, that sounds pretty good as a first approximation. So you have to have an expectation. You cannot make these processes go smoothly when you do not know what you're dealing with. So if you know the cable is 1,000 feet long, and this, for instance, you get this trace, and it tells you the open is 549, then you pretty much already found like one of your faults, because it's 1,000 feet long, and the TDR indicates otherwise. Speaking of the cable velocity, the pulse that the TDR is sending out is traveling at a percentage of the speed of light, because there's a solid dielectric, and which is 60 to 70% of the speed of light. And a typical value for plastic cables would be 255 feet per microsecond. This is one number. For PILC, it's a little less, maybe in the 230s or something like that. The velocity is mainly affected by the insulation material, and also some other manufacturers, other parameters, like for instance the conductor size, because that all affects the geometry. See, for medium voltage cables, 255 is a good starting point, unless you know otherwise. If you actually know you have a certain type of cable in there and you have manufacturer information, you obviously dial in whatever the manufacturer rates its own cable. Now let's go to the arc reflection method. So with the TDR, you get a impedance footprint of the cable, and it allows you to a certain extent to identify low impedance faults because you have this downward blip that indicates a short or at least a very low impedance, so you get away with that. But as soon as the fault is larger than a few hundred ohms, then a TDR will not be able to see faults like that. A typical pinhole fault, this low voltage pulse is not enough to bridge the air gap from the center conductor to the concentric neutral. So you have the TDR is blind for pinhole faults, just the TDR by itself. Now there's a method of utilizing the TDR in a way to actually see the position of the fault and to give you a distance to the fault. And this is called the arc reflection method. Today this is a group of methods because there's obviously development on that end. But in general, all of these methods have a few things in common. You have a high voltage source, you have some sort of filter, you have the TDR that is in that circuit for visualization and for measurements, and you hook this combination up to a cable, and then you execute the arm. And the arm is a two-step process. So you combine a low voltage signal with a high voltage surge. You record two traces and you overlay those two traces. The first trace is the low voltage trace purely from the TDR, from the radar, and then you discharge your high voltage source into the cable and you record a measurement of that, and you overlay those two, and the point where the two traces are deviating, this is the location of your fault. So what role plays the high voltage pulse here? The high voltage pulse creates an electric arc at the fault position, which sparks and then turns into a kind of weak electric arc. And the TDR is constantly sending out pulses, and these pulses are bouncing back from that arc that wasn't there before. And because that arc, there's a current flow related to this, and it is a very low impedance situation. It's a short. It's an arc. There's two electrodes, two different parts of your cable that should not be at the same potential now are almost at the same potential. So the TDR will record a downward blip, a downward bump, and with the overlay of those two traces, you can actually calculate the distance to the fault. Now, how does this look? Let's take a look at our cable, and we have a fault somewhere. So you have the beginning of the cable, you have the end, the physical beginning and the end, and there's this fault location somewhere that we don't know yet. So you do your low voltage TDR trace, your reference measurement, and you will get something like that. The TDR is blind for the pinhole fault. It sees the end of the cable. Now you discharge your high voltage source into the cable, which creates that red trace, and those two traces are hugging each other. The moment when the high voltage surge reaches the pinhole fault, it will flash over, create this downward signature. You overlay these in software, and the software will calculate the distance to the fault. And this is how you actually prelocate that type of fault. So real traces look a little bit like this. So on the very top, you have a typical pinhole fault. So the traces are pretty much, not exactly, but they're very close to each other, hugging, especially in the beginning. And then you have this sharp V-shape signature, downward signature, and the computer flagged it at 7,990 feet. There's your flashover, and this is where your cable fault is. Now on the bottom you have a different type of fault, and this is a fault right at the end of the cable. That would look like that. So the traces are hugging each other perfectly, and then at the fault they will deviate, and this is where you will find your fault.
Oh, Robert, we had a quick question I wanted to throw in there while I get a chance. The question is, what does the runtime factor of a TDR refer to?
The runtime of a TDR?
The question is, what does the runtime factor of a TDR refer to?
The runtime factor. I'm not really familiar with that expression. Are we referring to the cable velocity here? I don't know. Maybe Henning has to help me for the first time today.
Well, I think yeah, I agree with you. I would think it has to do with the cable velocity, because it's really the factor that the pulse travels along the cable. I think that would be my interpretation. Typically, people refer to as velocity, but propagation velocity. But I think runtime factor is pretty much the same, because it tells you how long it takes for the pulse to run back and forth on your cable. So I would agree with you. It's cable velocity. I think that's what it's referring to.
Okay. So let's go to this filter problem real quick. So why do we have a filter there? And the reason for this is you have the high voltage source, which is pretty much a capacitor. You charge the capacitor, and then you run this energy through a filter. So why is that? That was the last of the bullet points on this other slide. So why do you do this? The reason is you want to maximize the chance that one of the radar pulses is actually hitting that arc when it's standing there, when it's burning there, for only a few milliseconds, and so you can actually see where the fault occurs. These TDRs that are involved in fault location are not your typical handheld TDRs. Those are triggered TDRs. So now, if you think about the longer the cable gets, the more the runtime differences between like the TDR pulse and the actual discharge of the high voltage source can become a problem. So the TDR has to be timed very precisely to actually hit the standing arc to reflect back. There's a few different ways to do that. The most primitive one is a passive resistive filter. So you just have a resistor in line with your source, and you can see where it says surge voltage, the steep, almost needle, that is what the high voltage source, the surge generator, the thumper, is putting out. With the resistive filter, you're already extending the time. Then you have a semi-active way of doing that, and you have a coil, an inductor there, which already extends the time the arc is present at the fault. And then you have a technique where you actually discharge an additional capacitor on top of your main capacitor, and that would be considered active. And people refer to this as double surging. And one variation of that is the ARM plus. So there you can see why there is a filter for the arc reflection method. Actually, it is to make it possible to actually gain a good radar reflection from the fault position. Now let's summarize. With the prelocation, you try to learn a few things. First of all, the distance to the end of the cable. And when you are not sure about the distance, when you're not sure that you actually have the physical end of the cable, what you can always do, hopefully, is that you send somebody down to the other end of the cable, if it's doable, and physically short the conductor and the concentric neutral together, and the live TDR trace should go from an upward signature to a downward signature, because you go from an open end to a dead short, and the TDR indicates these with different signatures. So if you're not sure if you have the actual end of the cable, you can always verify by physically making that connection, so you actually find the end of the cable. Because this is very important. To find the end of the cable is one of your main priorities when you want to attack these problems, because as we had in this example before, the cable is 1,000 feet long and the TDR flags it at 550 open end. What is going on there? So a way to verify is, if possible, short the two at the end together, the conductor and the concentric neutral, and see if the TDR trace changes. That already tells you a lot. So with the distance to the end of the cable, what you pretty much want to do is you want to eliminate any awkward situations, surprises. You really want to know with what type of fault you are dealing with. You will get, by using the ARM methods, a distance to the fault. So it will actually tell you fault this far out from where you are. And you can also gain additional information, which could be like a webinar by itself, for like to count, or to identify, it's a better word, to identify splices and transformers. So you can use the arc reflection method. It's a very powerful tool for sectionalizing, actually, because you get the distance to the fault and it puts you between two transformers, and then you know which segment of your cable to isolate, to sectionalize. Now, when we have this prelocation and it's fairly accurate, why do we have to do pinpointing at all? And here is what I already mentioned before. The velocity of propagation, the cable velocity, can be a systematic error in your doing. If you have the wrong velocity, you can be off, and to actually dug a hole, not being sure where the fault actually is, that is gambling. You can also the cable path is of importance, because the TDR gives you a distance of the fault. If the cable is not following the actual path, let's say classic example is the crew thinks you're standing at a pad mount transformer, the cable runs down on your side of the road to the next pad mount, while in reality it crosses the street to the left, runs on the other side of the road, and comes back under the asphalt, under the pavement, back to the other pad mount. Now, then the distance is correct, but it's physically at a different spot because the layout of the cable is different. And also the problem why you have to do pinpointing is you always have the possibility, the nasty situation that you have multiple faults on the same cable. Therefore, you apply a process that is typically referred as thumping, and you assist the thumper by using a pinpoint device. So just if somebody is not familiar thumping, what is thumping? You have a high voltage source, a surge generator or thumper. You charge up a capacitor in that high voltage source, and you discharge it abruptly by closing a switch into the cable. And this is a very high voltage, high frequency, high energy pulse, and that travels down the cable. In this case, it is not filtered as before. While the arc reflection, the prelocation, is filtered, the thumper or the thumping is done at an unrestricted energy level, so to speak. And if you would demonstrate this in air, you have a short cable, and you do an arc reflection to demonstrate this to an audience, and then you do a thump, while the arc reflection is only a kind of weak sizzling, the thump is actually like a gunshot. So it's really loud, and it's actually really powerful. So what does this pulse do? Well, it travels to the fault position. There it flashes over. This is why it's important to thump at a voltage above your formerly learned breakdown voltage. Otherwise, it won't flash over. The thump will flash over there, and this creates sound, noise, and also an electromagnetic field is surrounded by this electric. Or the electric discharge is surrounded by an electromagnetic field, and you can use this actually for a very accurate pinpointing. So when we're talking surge energy, because if you look up any specs, thumpers are always, one of the main specs is the energy. So why is that? Well, energy is measured in joules, and that is watt seconds, and joules equal noise. The threshold for actually hearing a surge in the ground is typically 300 to 400 joules, and it is very unlikely that you will pick up anything if you have insufficient levels of energy. And a typical value for URD cables, your you would be doing very well if your thumper has 1,000 or 1,500 joules. Now the surge energy of the thumper, as I wrote there, is proportional to the capacitance C and to the square of the voltage. This has certain implications for the practical application of those thumpers. Back in the days, and a primary example of that was always Biddle, they had huge thumpers, insane energy levels, but they were only single stage. Modern thumpers are typically multi-stage, and the reason is to provide a high energy at various different voltage levels. Because if you, let's say, have a thumper that can go up to 16 kV and 16 kV only, there's no lower stage, you will only get your maximum energy at that voltage. Now, because the energy goes with the square of the voltage and not just with the voltage, if you thump at 8 kV instead of the full 16, you cut your energy, the energy will be a quarter. Not half, it will be a quarter. That means the lower you go, the less chances you have to create noise. And this is the reason for the introduction of multi-stage thumpers, which are standard today. So you have choices, and one very practical choice, always thump at the lowest possible voltage to get the maximum energy out of it. Of course, you still have to make it flash over, and if you are above the rating of one of the stages, well, then you can't help it. But if you have a multi-stage thumper, let's say 8 kV and 16 kV, it flashes over at 7, be in the 8 kV stage to actually utilize more energy. Don't be in the 16 kV stage, because 7 is even less than half of 16, so you will drastically diminish the energy you can pump into the fault to create noise. Why is the creation of noise a problem? Or why are we doing this? Because the pinpointing devices can pick up either on the sound or the electromagnetic field. So the noise is pretty much, or the thump is the source of what you can pick up then to pinpoint the fault. Another thing I just want to mention real quick is the capacitance. Typically, the thumper has to be sized properly to be able to actually charge the cable. And the typical rule of thumb there is that that the thumper has to be 5 to 10 times the capacitance of the cable you want to thump to really make sure you have enough energy to dump into the cable. Because as we saw before, the cable is mainly a capacitor, and you have to charge the cable. If you're not able to do that, then you will run into problems if your thumper is too small. Now, pinpointing devices. Why are we doing that? Technically, you could just thump with a high energy, and you can thump for hours or days, and you can just walk along the cable until somebody picks up the noise somehow. Well, this is not a preferred way of doing that, because these thumps are done at typically at a fairly high voltage. So the longer you stress the cable, you risk of getting into something. So the pinpointing device actually reduces the time that you need to be surging. So from your prelocation, you already know, you have an idea plus minus 1% where the cable where the fault is located. You walk in the proximity of that. You tell your crewman to turn on the thumper. You bring your pinpointing device, and you will find the fault fairly quickly, and there's no need of thumping around for hours. Older methods were purely acoustic, and the problem with that is that as soon as you run into concrete or different soil material where the sound waves are propagating at a different speed, or in very noisy environments right next to a road is a classic example, you can run into problems there. So the method of choice today is the so-called coincidence method, or simply called the thunder and lightning. And it's the same idea. The electric discharge that the thumper creates is your lightning strike, and since the electromagnetic field travels way faster than the sound, you can pick up the electromagnetic field with the coil first, and then you can detect the first sound that travels through the soil or the concrete, the pavement, whatever, and then you compare those two, and then you can calculate a delay, and then you go a few feet ahead towards the assumed fault, and then the pinpointing device will indicate to you, hey, did you get closer or did you get further away? And for that purpose, you can get to the fault fairly quickly. And since these coincidence devices, they are based on the first sound, they also don't get fooled by conduits, because the ends of the conduit is typically where the biggest noise is that a human would run to, but the computer cannot be tricked with an algorithm like that. So here you can see on this illustration there how it actually works. So there is a search generator, a thumper. It's hooked up. The pulse travels down. So the red is the electromagnetic field, and then there you have the noise that is created at the fault, and you can pick it up with your pinpointing device. Now this is one of the examples that, for instance, Megger has at the Digiphone Plus. Is the pinpointing device. Well, this is the last slide now on the topic. I just want to say something about burning, because I run into this question or this thing fairly often. Burning, just to clarify this, burning is a technique that was invented for PIL cables, for paper insulated lead covered cables for the laminated insulations. The reason is, when you try to create an arc, the oil is moving particles, so it's really hard to ignite and sustain an arc in conditions like that. So what you try to do with the burning is you try to condition your fault. You try to carbonize the fault location. You carbonize, you change the chemical properties of the oil, and you create a carbon path, like a track. And therefore, the resistance of the fault is reduced, and then you can use the arc reflection method. You displace the oil, you introduce carbon, you reduce the resistance, therefore, and then you can apply the arc reflection method. And therefore, this is a typical PILC fault locating technique. It is not. It is on plastic cables. It is really your last stand, because it can actually really harm your cable. It will heat up your cable that a large amount of current that is also there for a long amount of time can actually melt the insulation at a certain point, and then your concentric is actually trying to slowly wander towards the conductor. And if you're lucky, you create a situation where your TDR can pick it up, or where you have the chance of thumping. But where do you stop? You don't know where to stop. So in most of the cases, when people try to burn plastic cables, they literally burn it like to death. They burn it open. They carbonize it into a condition where it's really hard then to go on with actual fault location. So be very careful with burning. It's a typical conditioning technique. You want a permanent conversion of your fault for laminated cables, not for extruded cables. So what has Megger to offer? Just a few things. On the left, you can see some radars, TDRs. Then we have on the left lower corner, it's the Easy Thump. It's a small thumper, 12 kV system. In the middle, you see one of the bigger units, a 16 kV dual stage thumper, 1500 joules. And on the right, then you can see a system that is probably more convenient for downtown network fault location. This is an SWG 3500, so you have a surge generator and additional capacitor to provide you more energy. On the right, you can see the filter that were talked about for arc stabilization, and on top you can see the radar. This is a heavy, a typical van-mounted system with very, very high energies that you need in those downtown networks or for PILC cables. And if you want to know more about the product line, this link will help you. And the another thing that I can suggest looking into is an integrated van system. For instance, here the Centrix 2.0. These can be configured for diagnostic purposes, but also for fault location purposes, or for both. Like, for instance, this van has both. So then you can have all kinds of. This is pretty much an entire toolbox integrated with one software and one interface that can do fault location and diagnostics. That is the very high end, the flagship solution, the so-called all-in-one solution. That this is an actual toolbox that will provide you every method that there is to be able to handle cable faults or to do diagnostics. And that was that. And thank you for watching.